Hello, this is Fireworks by James Sinclair, part of his Artisanal Sudoku Volume 114, I think? 114? Yes, Volume 114. Okay, this is the first puzzle, so let's take a look at the rules. Normal Sudoku rules apply, so place the digits 1 to 9 in every row, every column, and every 3x3 box. Killer cages. So, the sum of digits inside each cage is equal to the small number in the top left corner. So for example, those digits sum to 7 because 7 is in the corner here. Those digits, for example, sum to 5, those digits sum to 10, and so on for the rest of these cages. Arrows, the sum of digits along an arrow is equal to the digit in the connected circle. So those two digits on the arrow, those sum to whatever's in here. If this was a 6, for example, then those digits would have to sum to 6. And also, digits in cells separated by an X sum to 10. I don't know. It was said that the X's in this puzzle actually, they are not required to solve the puzzle. So the puzzle is actually unique without the X's and is solvable, even though it would be slightly harder. I might try ignoring the X's for now. Unless I actually decide I have to use them. But yeah, they're not required. But just for clarity, digits in cells separated by an X sum to 10. So those two digits, for example, sum to 10. Those two digits sum to 10. And those are all the rules. With that, let's just begin solving. Right, so I can begin with this 8 here because it is on a 3 length arrow. And those 3 digits are all different. So if those digits have to, actually it doesn't even matter if those digits are different or not. Because those digits sum to 8, that digit is at least a 1. Right? Because you must place 1 to 9 in every box, I guess. The point is that those digits are now at least a 9, but cannot be any higher than that because this single digit cannot be higher than 9. So it in fact must be a 9, which is made of 8 and 1. Now we can actually do the same for the rest of these. That sums to 5, so that must be a 4 to make a total of 9. That sums to 6, so that must be 3 to make a total of 9. This sums to 7, so that must be 2 to make a total of 9. Oh, we can do the exact same in this corner because that sums to 8. This is at least 1, therefore this is at least 9 and must therefore be just 9. We can do the same for the rest of the arrows actually. Yeah, this 7 means now this is a 2, this 4 means this is now a 5, this 5 means this is now a 4. So yes, already a lot of digits, so that's cool. The 4 cage is very interesting. There are only two ways to make, there's only one way, sorry, not two ways, one way to make a 4 cage work. It is with 1 and 3, and because of this 1, that is resolvable. Okay, what about this? This 5 is also resolvable because there are only two ways to make 5 in 2 digits. It is either with 2 plus 3 or 1 plus 4. Now since that digit can't be 2 or 3, it cannot be a 5 cage with 2 and 3 in it, it must be with 1 and 4. Therefore the 1 can't be here, it must be here, and the 4 must be there. Cool. Can we do the 7? I think we can. The 7 also has 2 digits only. Sorry, 2? No, it has 3 possibilities. It is either 1, 6, 2, 5, or 3, 4. However, because of the 1 and the 5 here, this cannot be 1, 6 or 2, 5, it must be 3 and 4. And the last one is an 8. I don't know if we can do an 8 though. No, we cannot do the 8. The 8 is not resolvable. They can be either 3, 5 or 2, 6, I think. Alright, let's keep on moving then. This 4 does help us with this 5. Because this 5 now cannot be made of 1 plus 4. It must be made of 2 plus 3, and that is resolvable. This 6 is probably helpful. Yes, because the 6 is also having only 2 options. It is either 2, 4 or 1, 5. It can't be 2, 4, so it must be 1 and 5. Can't resolve yet, but probably not too much of an issue. Okay, I'm very tempted to put a 6 here, which would help in a lot of different areas, but because of the X not being required, I'll leave that alone for now. Okay, what else can we do? We have a lot of low digits. What about high digits? Are they restricted? I mean, not necessarily, right? No. Okay. Well, what can we do here then? I can't believe I'm already stuck. I mean, I wouldn't be if I had this X to use, but I don't want to use it. I just refuse. This maybe? It can't be 3 or 4, so this 7 is now no longer a 3-4 pair. It still could be 2-5 or 1-6 though, I think. The author said that this puzzle will be bumped up to like 5 out of 10 difficulty without the X's, which I still think should be doable. Maybe we'll look at the 7 and the 8. Yeah, in fact, we can look at the 7 and the 8. That's very interesting. Because the 1 mean that those digits are now at least 2, 3, 4, and 5, which sum to 14. And because of the 7 and 8 here, those sum to 15, which at this point will only have one option left. So let's take a look at why that is. Let's take a look at the minimum digits we can place in those 4 cells. They are 2, 3, 4, and 5. Now that sums to 14, but we want 15. So we need to increase one of these digits by 1, but because they all occupy the same box, they cannot repeat. Therefore, you cannot increase 2 by 1, you cannot increase 3 by 1, and you cannot increase 4 by 1, because all of those, when increased by 1, will give you a duplicate digit. The only thing you can increase by 1 is 5, which gives you 6, and that does in fact sum to 15. So now, those digits are therefore 2, 3, 4, and 6. We can do even better though, because we can say, where does 4 go? Well, 4 can't be in the 8 cage because it requires another 4 to make 8, which doesn't work. So the 4 must be in the 7 cage, which must be paired with 3 to make 7. This 3 resolves that. I'll put big digits now. Now those remaining digits have to be 2 and 6, which do in fact add to 8, and is resolvable with this 2 over here. This 3 resolves this 3-4 pair, which should give us a 4 in this box. It does. 4 is now here in this box. I was eyeing that for a moment. I was like, if it could resolve this, we could put a 4 in this box. But alright, that is a pretty cool piece of logic. I've seen it used with other things as well. I've seen it used for 5 and 6 cages. I've seen it used with 14, 15 cages. But never actually with 7 and 8 cages. So I think that's cool. Now what? We probably have a lot to go off of. Maybe. 2 has 2 positions in this box. Can we figure out the 8? Yes, we can. In fact, yes, because of the 3s here, we can now figure out the 8. And the reason is because the 8, now without any 3s in it, cannot be 3 and 5. It again cannot be 1 and 7. It can only therefore be 2 and 6. That is resolvable by the 2 up there. Nice, that's very clean. I could probably put like... no, I can't put... I was like, can I put a 3 in this box now? Not yet. But probably close to being there. Whoa. Is this music getting loud? Kinda loud. I think I can speak over it, but I'll tone it down a little bit. Hopefully that toned it down enough. Actually. Good enough. Alright, let's keep going. Let us just keep going. Ones? Well, ones form some sort of X-wing here. 5s are just awkward. Well, where does 5 go in this column, now that I look at it? There's a 5 in one of those cells, so those can't be 5. 5 here sees that cell, so none of those cells are 5. 5 must be here in this column, therefore. I also saw it because of this fake X-wing looking structure here. I don't want to explain it right now. I assume we'll eventually hit an X-wing somewhere throughout this video. Okay, so what next? I guess 2s? 2s might be useful. Not really. I assume it's something to do with those cells. But I can't really see how. What does 6 go in this box? 6 goes in one of those 2 cells. That doesn't help. It wouldn't help. Okay, maybe those digits? Not really. We again know it's not 3, 4. It still could be 1, 6. It's still entirely possible. I can't say that this can't be a 1, right? Technically, because I don't know that the X is here, I choose to not see the X here. I could technically put a 1 here right now, And so far it would look correct to me, even though it's obviously wrong. I want to find some other way to prove that this is a 6, or at least not a 1. But right now I can say that 1... Well, where does 1 go? 1 can go in several positions. 2 going here. Okay, well, let's think about this. How this interacts with those. Because those sum to 9 and those sum to 10, that digit is always the common digit. You can tell that this digit is always going to be 1 greater than that. Because this digit is 10 minus this digit is 9 minus this. And so doing a bit of math, this is always 1 greater than that. Similarly, this is always 1 greater than... this is always 2 greater than that, actually. So maybe we can figure out a couple... no, I don't think we can. No, there's nothing much there to look at. Wow. I guess there really isn't much. Do I really want to use the X right now? I mean, I guess I could. But if this puzzle is solved without the X, I would like to not use it. I guess 4 and 3? 4 and 3 can't be there. We know this now can't be 4 or 3. That leaves 4 and 3 in a number of possible spots. So I guess I'll mark those down. We'll try and analyze those. This being 3 or 4 means this is either... That will either be 6 or 5. This one as well will also either be 6 or 5. Which means that putting a 3 here is technically probably correct, but I can't tell you why. This doesn't have any effect on anything. Yeah, I don't really see much else, really. Wow. Okay. 5? I mean, 5 can't be in the 10 kit because it can't have another 5 with it, so I guess that happens. 5 can't be... No, 5 could be here if 4 is here and 2 is here. So 5 could be there. 5 in here puts a 4 there, which is fine. 5 could be there or there, doesn't really matter what happens after that. So yeah, 5 still has a lot of options. Okay. I'm gonna have to like bite the bullet and use the X soon if I don't see anything else. Okay, I guess I can place like... I can place like 7, 8, 9 here. That's a triple. This also forms like a quadruple of some sort, like 6, 7, 8, and 9. Can't do much. There. This is 5, 7, 8, 9 quadruple. Alright, I'm giving up. That's a 6. We just put a 6 over there. That must be 3, that must be 7. Good enough. I don't want to think about this anymore. Okay. 6, 3, 7. Cool, because well, I mean, this had to be a 6 because of the X. And because of this 6, this must not be a 3 because of the 9. Because of the 3, this must not be a 7 because of the 10. This now can't be a 7, but at least you have a 7 to work with. Is this going to be any easier now that I've done this? Probably. Maybe. Like, because of the 6, this now can't be a 1-6 pair. It cannot be 3-4 either, so it must be 2-5, sorry. And this 2 resolves that. 5 means this must be 4. Those digits are therefore 1 and 8 to finish the box. 1 here resolves that. Okay. 7 can't be in those cells, so 7 must be there. 8, 9 pair. This is a triple? Yes, it is. It is 5, 7, and 9. I think at this point we're just done with all the clues, so it's all just regular Sudoku now. Nine can be here. This digit could be anything. Okay. 5 can't be in those, also 5 must be here. Cool. 5 can't be there or there, so 5 is in one of those cells, which forms an X-wing appropriately. Those digits are a triple, they have to be 7, 8, and 9. Therefore we have more triples here. Those are 1, 2, and 8. Actually, yeah, this is resolvable. 1's here mean 1 goes up there. 2's here means 2 goes here. 8 now goes down there. Those digits are 3, 4, and 6, I believe. 3 and 4 mean that can't be those, so they have to be 6. 4 here means this is 3, so 4 goes there. Nice. Those digits... Well, 6 can't be there anymore, so in this box, 6 must be here. Those digits I was going to say form a 7, 8, 9 triple. And that digit can't be a 9. Actually, this forms a... Oh, it forms a 5, 7, 8 triple. Right, and this 8 removes 8 from those cells, so 8 goes up here. Cool. This forms a 5, 7, 8 triple as well. And, 5, 7 pair here means this must now just be 9, which resolves basically everything, I think. 5, 7 means this is 9. Those can't be 5. This digit must be just a 3 to finish the box. That's clean. This is a 7, 8, 9 triple. Don't know if that does anything. 8 can't be in there. I don't think so. I don't think so. Okay, now what? This forms a triple, I think? Yeah, that forms a triple. They're just 6, 8, and 9. And in fact, they're just triples everywhere now. 9 can be here. Those just are 2, 4, and 5. Is that resolvable? Yep, 2, 4 means that must just be 5. 4 here resolves the remaining 2, 4 pair. Those are just our 1, 7, 9. 1s resolve the 1 over here. 7, 9 is still a thing, but that does form a pair, so that's nice. And those digits are now 3, 6, 8. 3, 6 resolves that. 3 here resolves everything else. That digit is now, well, 5 resolves this 5, 7 pair firstly. That digit is now just a 9 to finish the column. 7, 9 pair means that digit is simply a... can't make any mistakes here. 6 to finish the column. Those digits, well, 9 firstly resolves this 9, 7 pair. Those digits are just 2 and 8 to finish the box. And this 2 does resolve that. So this is right, this does add up to 8, which is good. 8 resolves this 8, 9 pair, which puts a 6 here and a 9 over there. Okay, we're getting this done. 9 means that can't be 9. That can be 8, and that can be 7. Classic. And by classic, I mean classic chocolate teapot. I'm gonna melt the chocolate teapot at this point though, because 9 resolves this 8, which resolves everything else. I'm melting the chocolate teapot. Anyway, those digits are now 5 and 7. It's gonna be part of the final disambiguation, right? This is 1 and 6. Yes, 6 resolves this. 1 resolves this. 5 resolves this. And 7 resolves this. Nice. Solved the puzzle in 18 minutes and 9 seconds. Cool puzzle. I spent a bit of time trying to figure out what to do without this X here, but I gave in eventually. It's okay though. Hope you enjoyed this video. I'll see you guys next time. Bye bye. Hello, this is Steerage by James Sinclair, part of his Artisanal Sudoku volume 114. Alright, so we got thermos this time. So let's look at the rules. Normal Sudoku rules apply, so place the digits 1 to 9 in every row, every column, like that, and every 3x3 box. Killer cages. So we have some killer cages here. Those mean that digits in killer cages sum to the number in the corner. So those digits, for example, sum to 30. those digits sum to 11, those digits sum to 29, and so on for that last cage. Right, what else do we have? Well, digits, we have thermometers here. Digits on thermometers must increase from the bulb. So you have a sequence of numbers going along this thermometer. They must be in increasing order from the bulb. So they don't have to be increasing in any particular order. They just have to be increasing such that every digit is greater than the previous one. And finally, we have squares. So each square over here must contain an even digit. And that's it. 2, 4, 6, or 8. So yes, with that, let us just begin solving. Well, now, first thing I notice is that all these cages are very extreme. So if you look at them, each of them have only one option each. Let's start with the 10 and the 30. The minimum you can put in 4 digits, because digits cannot repeat in cages, must be 1, 2, 3, and 4. And 1, 2, 3, 4 do exactly add up to 10. Therefore, those digits are exactly 1, 2, 3, and 4. For the 30 cage, the maximum you can put in a cage is 6, 7, 8, and 9. And those add up to 30, which means that this must be exactly 6, 7, 8, and 9. Now the 29 and 11 cage also do only have one option each. And the explanation for them is slightly less straightforward as these, but they're still easily doable. We start off with the idea of the minimum here is 1, 2, 3, and 4, which add up to 10. To get 11, you need to increase one of these digits by 1. Doing that to 1, 2, and 3 will give you a duplicate digit, which doesn't work. Therefore, you must increase 4 by 1 to get 5. And that's how you get 11. And actually, this is a trick that we learned in the previous puzzle, or a trick that I used in the previous puzzle, to combine the 7 and 8 cages together. Right, now this 29 is the same thing, where it's taking 6, 7, 8, and 9. We need to decrease one of these digits by 1 to make 29, and the only one that does that without repeating is a 6, which turns into a 5. So here you go, 5, 7, 8, and 9 in this box. And we already have a bunch of quadruples over here. So let's start working on the thermos. In fact, the longer thermos might be more useful. Those digits, for example, have to be at least 3. And that's because if you make this at least a 1, going up here, this will be at least a 2, that will be at least a 3, and this must be greater than that. So those digits are at least 3, and therefore can only be 3 and 5. Those therefore must be in increasing order, 3 and 5. Whoa, 3, 5, I don't know why I pressed 4 like twice. Those digits remaining are 1 and 2 to finish the cage. And those digits are less than 3, which must be 1 and 2 in order. So now those digits cannot be 1 and 2 anymore. 3 resolves that. And this 3 actually is on a thermometer. So this 3 just goes down back to 1. Because it's the minimum you can have. That digit is also a 1 to finish the cage. This 2 resolves this 1, 2 pair. And yeah, wow, that's actually a lot of progress done with just this deduction. You can already do that on the opposite side. Yes, those digits are now 7 or less because this is at most a 9. If this is at most a 9, this is at most an 8. Then therefore this is at most a 7, this must be less than that. So those digits are 7 or less, which means they are 5 and 7 in increasing order, 5 and 7. Those digits are 8 and 9. Those digits must be greater than 7, which have to be just 8 and 9, which must be in order, 8, 9. That digit and that digit, those have to be 6, 7. This 6, 7 pair means those digits are 8 and 9. 8 and 9 here. Actually, is this the same thing? Yeah, this 7 resolves this. This is 6, this is 7. Which now means that those digits are greater than 7, they have to be 8 and 9 in order. This is now a 9, this 8 resolves this 8, 9 pair. Yeah, and we do the exact same thing. Okay, what else can we do? I mean, that isn't very helpful right now. I guess we could place what possible digits can be there. We know a shaded square has to be either 2, 4, 6, or 8. This can't be 2, so this must be 4, 6, or 8. This can't be 8, so it must be 2, 4, or 6. Which doesn't really help, so let's just move on. I got it. It's this. That digit cannot be 9 or 8, so at maximum it is a 7. But because of this 5, this is at least 6, and this is therefore at least 7. If this cell is at least 7, and at most 7, it must just be 7. Which means this must be 6, is the only thing between 5 and 7. You can probably do the same thing over here. Right, because this digit is at least a 3, it can't be 1 or 2. If this is at least a 3, yes, this 5 means this is at most a 4. This 4 means this is at most a 3. So if this is at most 3 and at least 3, it just is 3. And then this is 4. I guess that does help. This now can be a 6. And that now can be a 4. You know what? This also feels very X windmill. Like, look at those digits. Every digit that is the opposite of each other rotationally, they all sum to 10. I'll say this is therefore a 5. I can't prove that. It just, by gut feeling, I think it's a 5. Obviously, I'm not going to put a 5 there just because I think it is a 5. I've got to prove it first. Alright, let's keep going. This might be where it gets tough because this thermal is actually particularly difficult to break down. This could be as low as a 2. It can't be 1, but it could be as low as a 2. It could be... well, I don't know how high it could be, but because there are 4 other digits are greater than it, those digits... because those digits can be 9, they are at most 5, 6, 7, and 8, right? And therefore, because this digit must be lower than all of them, this digit is at most a 4. And therefore this is either 2, 3, or 4. But it can't be a 4, so it's either 2 or 3. If it's a 4, it will be 5, 6, 7, and 8 here, but... no, it's not a 4. Okay. I realized that that digit will be particularly high. That digit will be particularly low, in fact. That digit is at most a 5. It could be a 4 if you go 2, 3, 4, so... but it can't be any lower than that, right? Because any lower and you would need... yeah, any lower and you would reach a 1 over here. So this is at most a 4. And those are between 2 and 5, so they're just 3 and 4. 3 or 4, I guess. So this system seems to make sense to me. I don't know if we can resolve that system. But I guess now that this can't be 5, I've just disproven myself into saying that this is X windmill. It's not. Because in X windmill, where every rotationally symmetrical digit sum to 10, this digit must be a 5. It's not a 5, so... alright, I should not get ahead of myself. Try and continue solving this puzzle. 8s. My brain is thinking we do some regular Sudoku over here. 7s, in fact, yes, we can do. 7 goes here. And I believe 3 does the same thing. Yeah, 3 is coming there, so 3 goes here. Which means that this is now a 2. Awesome. Now those digits... well, they must contain a 1 somewhere. But 1 can't be in those cells, because those are greater than 2. 1 can be here by the box, so 1 must be there. Those digits are 4 and 8 to finish the box, and this 8 resolves that. 4 now places a 3 here, so that's cool. That digit remains 4 or 5. This is a triple, consisting of 5, 8, and 9. This must be 9 because it can't be 5 or 8. Which gives us a pair over here. I don't know if we can resolve that. Yes, we can, because of the 5 there. And those digits are 1, 2, and 6. In fact, this can't be a 1 because this forms a 2, 6 pair in the box. This 2 resolves that though, so that is all cool. Those digits can't be 2 anymore. This 6 resolves the 1, 6 pair. And those digits form a triple, so I didn't even see this. I thought this was filled. They're not filled. This is, I think, 4, 7, and 9. Yeah, 4 can't be here, this can't be 9, that can't be 7. forming a very nice chocolate teapot. I think this could be 7 if this is an 8, so no issues with that. This 8 though, sorry, means that can't be 8, that's 4. This 2 means now that is a 6. I could probably start doing regular Sudoku at this point. 3s, for example, must be in this box. This cell, sorry, not box. Box is the 3x3 thing. Okay, what else do we have? 2? No, 2 would be in 2 positions in this box. Is this a triple? Yes, it is 4, 5, 9. Ooh, but those digits can't be 4 because of the 4 in the box, meaning 4 must be here. That resolves everything. 7 must have an 8 here because this is greater than 7 but can't be 9. So that's 8. That forms a, I think, 4, 5, 6 triple. Those can't be 6, so 6 must go here. That digit to finish the box would be a 7, which means those digits have to be 1 and 2. Nice. I don't know if I can resolve any of these if I'm like missing out digits or something. I don't think so, so let's move on. This is now 3, 4, 5. 3 can't be there, but everything else goes. Those digits, 5, 6, and 7. 7 can't be here. 6 can't be here. This could be anything. Okay. I'm not seeing anything anymore. I think we should just keep going. Yeah, no. No, I almost made a mistake. That is not a good mistake to make. I almost thought this was not a 6 for some reason. Okay. Well, where does 3 go in this column? Yes. 3 is here and here, remove 3 from those cells, which means 3 in this column must be here. That's good to know, although I don't know how that would benefit. No, I don't see any way that could benefit. I could say 3 is in one of those cells though, in the box, but that really doesn't tell me much. Okay. Oh, we're slowly picking out stuff here, but I don't think anything would be very helpful. How have I figured this out but not this one? Is it because of the 7? I think it's because of the 7. Okay. Fair enough, fair enough. 4? No. 4 is in one of... 3s and 4s, there you go. 4 is in one of those 2 cells, but 3 is also in one of those 2 cells. So this forms a 3-4 pair, which does help. I don't know how it helps, but at least it's useful in some way. I think I could probably do the same thing here with like 5 and 6 or something, or 6 and 7. Yeah, 6 here is in one of those cells, and 7 is also in one of those cells. So this forms a 6-7 pair. I mean, I guess it could be useful because there are fairly few digits left. How did I get a 3 here? I forgot how I got a 3 here. It's like in this column, right? So how about this column? What digit are we missing from that column? 7? Yeah, what does 7 go in this column? Can't be here, can't be there. So 7 goes here. Interesting. I mean, this one was a triple now. I think they're like 5, 6, and 9. This can't be 5 or 9, so that is just a 6. This is now 5 or 9, which forms a pair. Nice. What else do we have? I mean, this is a triple, yeah. It's all just triples from here, huh? 5, 8, 9 as well. And same goes, this can't be 5 or 9, so that's also an 8. which means this is now a pair. They have to be 1 and 8. This 8 resolves that. There we go. We're getting in. This 1 means this 1, 2 is resolved. This forms a triple consisting of 2, 3, and 4. Okay, well, the moment I said that, 3 can't be there. The moment I said that, I proceeded to blank out. This forms a triple though. 2, 4, 5 triple, but this can't be 4, so that's 2 or 5. Forming another chocolate teapot. Very useful. 5, 9 pair. I didn't see that. 5, 9 pair means this cannot be 5, that is a 6. Those digits therefore form their own pair, 2 and 8 I believe. This 8 resolves that. This 2 means that is now a 5, and that should get us in for the most part. 5 means that's a 4, means that's a 2. This now can't be 2, that now can't be 4. This 4 means that's a 3, meaning that's a 5. This 4 resolves this 3, 4 pair. This 5 resolves this 4, 5 pair. This 6 resolves this 6, 7 pair, which then puts a 5 in there, which puts a 9 in there. And the last digit in this box is a 7, and this 9 resolves the 5, 9 pairs that started all of this. Cool, almost done. That digit is a 1 to finish the row, and those last 2 digits are 2 and 4. Yep. That took us 15 minutes and 39 seconds. Awesome puzzle actually. So yeah, I hope you enjoyed this video. I'll see you guys next time. Bye bye. Hello, this is Quarters by James Sinclair, the third puzzle in his Artisanal Sudoku volume 114, sorry. It is a fog of war puzzle, and I love fog of war puzzles, so let's take a look. Normal Sudokus apply, so place the digits 1 to 9 in every row, every column, and every 3x3 box. Correctly placed digits will clear fog around them. So, for example, if this digit was a 3 and I placed 3 in here correctly, all the fog around it will be removed to give me more information about what's underneath. Now, we have a lot of rules here that cannot really be shown, but I'll try to explain them with lines. So first we have Dutch whispers. So along orange lines, let's draw any orange line here. So let's say that's an orange line. Along orange lines, digits must differ from their neighbors by at least 4. So those 2 digits, for example, must differ by at least 4. So this is a valid way of putting digits on lines. Something like this is not, because those do not differ by at least 4. This is also valid, sorry, not that. This is also valid because they differ by 5, but 5 is at least 4, so that works. Next, we have purple Renban lines. So let's draw a line that's sort of pink but also purple. So that's a Renban line. They contain a non-repeating set of consecutive digits in any order. So actually, let's make this a bit shorter. Let's make it 4 digits long. This set of 4 digits must be consisting of non-repeating set of consecutive digits. So for example, 4, 5, 6, and 7. So something like this is valid because even though they're in random order, they do contain a set of consecutive digits. So those are not all the rules, but those are 2 of the rules. Those are all the lines. We also have here what appear to be the quarters of some circles shown, which is probably why the name of the puzzle is quarters. Those are part of quadruple circles. So a digit in a white circle, for example this 4, must appear in one of the 4 surrounding cells in that circle. So a 4 here must be one of those cells, for example. And each circle contains 4 distinct digits which are listed from smallest to largest. Okay, so that is where we're going to get all the information from. Right, so those digits, for example, okay, let's make this a bit easier. Let's say we have a Renban that looked like this. This is a Renban, not Renban. Let's say we have a quadruple that consists of those 4 digits. If those 4 digits are, for example, 1, 2, 3, 4, then the circle that is around, the 4 cells that are around the circle must contain the digits 1, 2, 3, and 4. And also, the circle firstly contains 4 distinct digits, which are listed from smallest to largest in reading order. So for example, a valid clue would look like maybe a 3, 5, 6, 9. This is valid because it is 4 distinct digits in increasing order. So yeah, those are, well, I hope I explained the quadruple rule well enough. Those are all the rules. With that, let's just begin solving. Right, okay, so we can definitely do something with the 4 here and the 6 here, because the 4 here is actually the last number to be read if reading order. And so because all of these digits are different, they must just be the digits 1 to 4. So here we have the digits 1 to 4, like that. The numbers, the digits you place in the cells do not have to be in the same order as they appear in the circle. But we can do the same logic here and say those digits are 1, 2, 3, and 4. Those digits are, because this is a 6, everything after it must be greater than 6, which are 7, 8, and 9. And because they are all distinct, they must be 6, 7, 8, and 9. Now, what can we do from here? I guess 5. My guess is 5 is the only one we haven't talked about yet. But that's I mean, those are equivalent. Those are a set of same digits, right? Ooh, those digits are all different, because if they were to contain, if any of those were to contain repeated digits, for example, those digits, let's say they were the same, then they would look into this box, and they can't be in those cells for as a result. Those digit, that blue digit must therefore appear in one of those cells, which isn't possible because we know those are 6, 7, 8, and 9, and not 1, 2, 3, and 4. So there cannot be any repeated digits in those cells, and therefore those cells must all be distinct. What's more, we know that those digits cannot be in there and cannot be in there. So those digits are in here, and therefore those digits, which are from 1, 2, 3, and 4, cannot be there and must be there. We can do the same for those digits here. And now we can place a 5, because where does 5 go in this box? Or rather, what digit is that? That digit is not 6, 7, 8, and 9, but because those digits are 1, 2, 3, and 4, because of the color, we can now say this digit cannot be those either. They must just be 5. Nice. Alright, and there's a Ranban line over here, which we know consists of consecutive digits in some order. Well, because this is a 3, right? It terminates at the end here. Yeah, this is only 3 long. This can reach anywhere from 3, 4, 5 to 5, 6, 7, but cannot reach any further because we have a 5 as a quote-unquote anchor point. So that digit cannot be as high as 8 or 9. I suppose another thing we could do is we could color those digits and say whether they go in this box. They can't be in those cells, so they must be here, which isn't as helpful, but we could do that. Same for those digits. Wait. No, that actually doesn't really help. I can say the same for those digits, which must be here, but that's overlapping colors, which is a little bit gnarly. So let's not do that. Oh, yes, I see. That digit must not be a 4, because this can only go down as low as 3, but cannot actually go down as low as 3, because if it was a 3, this would have to be a 4 to make a set of consecutive digits. This digit, therefore, cannot be as low as 3, but could be as low as 4. Well, therefore it has to be at least 4, sorry. And because those digits are from 1, 2, 3, and 4, which I might as well just mark down, that digit just has to be 4. So there you go. This digit is therefore a 6 to finish your set, which gives us a bunch more stuff. Actually gives us a bunch of lines over here. A few more Dutch whispers, I think? Yeah. Anyway, 4s now come in those cells, which is, it makes sense because blues are now 1, 2, and 3. I'm gonna draw your Dutch whisper, so it's gonna continue to look like this. At the very least. I believe it could branch off if it wanted to, but I don't know if that's allowed here. I don't think we need to know. However, yes, okay, I can say that this is a 5. And the reason why is actually because Dutch whispers are very special. They are, of course, less restricted than their cousins, which are the German whispers, but Dutch whispers do also have their own tricks. This, for example, is a high digit. It's 7, 8, or 9, which is very high. This is a low digit, which is 1, 2, or 3, which is very low. If this digit was too low, it would not be able to work with that digit, but if it was too high, it would not be able to work with that digit. Therefore, it must be somewhere in the middle. It must be a 5. And that's not proven, but I can sort of prove it by saying this is between those two digits, right? But it must be between them in such a way that it differs by 4 from both of them, at least. So those digits differ by at least 4, and those digits differ by at least 4 as well. That creates a total in which those two digits differ by at least 8. And the only way to make that happen is a 9 and a 1. And because of that, this digit must be right in the middle, a 5, which do differ by exactly 4 from its neighbors. So it must be 9, 5, 1. Nice. Now we can remove 1 from all the orange cells. Those digits are now no longer 9 either, forming a 7, 8 pair. 2, 4, huh? Well, 2 and 4, because we are increasing in reading order, the middle between 2 and 4 must be a 3 somewhere. So this must contain 2, 3, and 4 in some order. 4 come in those cells. So 4 is in one of those cells now. What else do we have? 9 is one of those cells. Although that's not very helpful. This digit is greater than 4. So in fact, oh no, I was like, so in fact what does 1 go in this box? It just goes there. That's forced. But whatever this last digit is that it's shown in this circle, because circles must contain 4 distinct digits, must be greater than 4, which cannot be 5 or... well, it could be 5 or 6 if they were up here. It can't be 5 because 5 is not in this area, but 6 could be up there. Or could it? I don't think so. No, okay. It's about those 4 digits, I think. Yeah. Whatever the last digit is, let's call it X. Whatever the last 4 digit is, that has to fill up this because 4 can't be in those two cells, but those two cells cannot be 2 and 3 because you would force those two cells to both be 1, which is impossible. So those can't be both 2 and 3. They must be only one of them. And because they are one of them, the other one will be up here along with the 4. And therefore the last digit would also be down here instead. So this contains 1 of 2 or 3 and 4. Not 4, and X, whatever X is. Which could be, well, it can't be 5 or 6, but it could be 7, 8, or 9. So yeah. Don't know what that means entirely. But alright. We have another Ranban over here, which I might as well just extend myself. I don't know if the colors work out very well, but hopefully they do. This is at the very least what they could extend to. They could extend further if they wanted to. But right now this is what we know. This digit can't be a 1. 5 is in one of those cells. Really? Really, what could those digits be? We don't know the last one, do we? Unless we do. Does the rule say anything special about them? They say 4 distinct digits from the smallest to the largest. Nothing about consecutivity or whatever it is. No, it's just that the last digit is greater than 4, somehow. Don't know how that would be useful though. Oh, I see. Because the last digit is in here, we know that that digit is either a 2, 3, or 4. In fact, those digits are all either 2, 3, or 4. Because we know the last digit is down here, it is not up there. So this digit being on a Ranban line does tell us something maybe. This digit, yes, this digit is like... it's either a 1 or a 6, I think. Because 2, 3, and 4 are here, this cannot be 2, 3, or 4. It is therefore either a 1 or something higher than a 4. And it can't be 5, so it's at least a 6. However, we know that if it's anything greater than 6, how could these be joined? Oh, it could be joined by a longer line. If your line was longer, you could have something like a 7 here with, 4, 5, 6, 7. So yes, we don't know how long this line actually is. All that we know is at least 3 long. But this could be a lot higher. Could also be 1, that's just possible. Oh, never mind, it is a 1. Alright, where does 1 go in this box? The 1 can't be here. We know 1 is one of those cells because this quadruple contains a 1 somewhere in it. The 1 is here, which must not be in there. So 1 in this box is just here. Okay, there you go. So yeah, this is in fact a 3 long. So I guess this can't be that far away. In fact, because of this 1, this just must be 2 and 3, right? Yeah. Alright, that makes sense. 1 must be with 2 and 3 to form your set of 3 consecutive digits. 4 in this quadruple can only be here as a result. Nice. This must contain 7 and 8 somewhere. That's 2 and a 3. 2 or 3, which is in the upper half of this circle. We don't know where it is, but we know 7 and 8 is somewhere in there. This 4 though means that this has to be at least 4 away, so it is at least an 8. But because 9 is one of those cells, that can be 9, so that's just an 8. Now 8 can't be there. And in fact, that digit can't be 7 or 8 either, can it? Because if it was, that would not differ by at least 4 from here. In fact, this must be... well, this must be less, 4 or less. To differ from 8 by at least 4. And it can't be 4, so it's either 3, 2, or 1. Therefore, 8 can only be here. 7 can only be here. Now 1, 3, 7, 8 means this can't be a 2, that's a 3. Pushes a 2 down here. Oh, we know it's a 7, huh? So those digits are now 3 and 7 to finish the quadruple. That removes a 7 from here, so that's 8. 7 goes up there. This is a 9 to finish the row. And everything else, well, 3 can't be here. So that forms a 1, 2 pair, which continues helping us. Yes, it does. This 1, 2 pair means that must be a 2. So that must be a 3. Those digits form a 1, 2 pair. And those digits form a 3, 4 pair because we colored them in. So hopefully that was right. I don't know if that's an accurate thing to do, but hopefully I colored it right. Alright, let's keep going. This digit is now just a 1, I believe, because it can't be 3, 7, or 8. 4, 6, huh? Okay, let's start with this 3. This 3 means that those 2 digits in the upper section of the circle must be less than 3. So they have to be 1 and 2. So we know 1, 2, and 3 are in this quadruple somewhere. The last digit we don't know. 1 can't be in those cells, so 1 is up here. Whoa. That does form an X-wing with this. So does a 2 actually. In fact, yeah, 1, 2, and 3 must be in those cells. Because 1, 2, and 3 all cannot occupy those cells. So those cells are 1, 2, and 3. Yes, alright, and in fact, I could probably work with this circle now, because those digits, whatever's in the circle in there, must be at less than 4. So they have to be 1, 2, or 3. Although we don't know which ones. I can't eliminate 1 from this quadruple, because 1 could be here. I can't eliminate 2, 2 could be anywhere, except there. Yeah, because those digits in the circle must be 1, 2, or 3, this must be 4 and 6, plus 2 other digits that are either 1, 2, or 3. Well, this can't be 1, 2, or 3 because of this over here, which means this must now be 4 or 6. Oh, this is a triple, I didn't even see that. This is a 5, 6, 8, I think? Yes, 8 can't be here. And I think that's just a 7 to finish the box. This is another triple, that is 6, 8, 9. That digit is not an 8. Oh, and this forms its own triple. This is a 4, 5, 6 triple. Nice. Okay. Right, so actually we know a 4 is in here somewhere, but this 4 removes 4 from those cells. That's how it can't be a 4. So 4 must go here. Nice. Cool, cool. The Renban extends upwards. And we know a 1 is over here, but we already knew the 1 is there with the 2. I think this fog of war is actually really well designed because it only reveals all the information that you need. It doesn't do anything to reveal anything that might give you extra stuff. So it's designed incredibly so that all the hidden information stays hidden, which is something I don't think I could ever do. But okay, so we now know this is 1, 2, 4, and 6. That now can't be a 3 then. This is 1, 2, and 6 in fact, just to finish the quadruple. 1 can't be in those cells, so 1 goes up here. And because of the 1 in here, this must be 1, 2, and 3. That can't be 6, so that's 2. 6 goes here. This must be 3 to finish the Renban. This is now 2, 3, 4, and 9, huh? Okay. So let's do that. 2, 3, and 4, and 9. So this is 2, 4, 9, because 3 is already used. 4 can't be there. In fact, 9 can't be there either, so that's just 2. This is now a 4, 9 pair, which resolves this 3, 4 pair. Cool. 3 is no longer in those cells. Something, something, something. Okay, what else do we have? We have a Dutch Whisper here, but I don't think we can do anything with that. Oh, we can. Sorry, this 7 resolves this 3-7 pair firstly. This 6 means that it's not a 6. And this forms a triple consisting of 5, 8, and 9. Right. And the only 2 digits from this set that do differ by at least 4 is 5 and 9. So they must be 5 and 9. That is now no longer a 9. It's an 8. So that is not it. We leave with a 6-9 pair. Nice. I think that digit is a 1. Although I can't prove it. Can I prove it? Yes, I can, just by regular Sudoku. This 2 means that must be 1. That must be a 2. By regular Sudoku, those digits cannot be 1. 1 goes here. This must be at least... Well, this could be a 9, couldn't it? 9 with 5 up there. Actually, both work. Wow. Okay. Are we done with all the clues? I don't think we're done with all the clues. I think there's something in here that we haven't figured out yet. But those are going to not be... we don't require them right now. We'll look at them later. Okay, what else do we have? I'm trying to stare at the screen. This is 6, 7, 8, and 9. Does that do anything for us? Not really. I don't know why this extends over here, because we already knew those differ by at least 4. So like this line doesn't need to be there technically. So yeah, it's just those 2 that give us stuff. Okay, I mean with this many digits we could probably do Sudoku. So let's try that, shall we? Let's try doing Sudoku. Ones, I mean ones do have a lot of options still. No, 1 is one of those cells, we've seen that. Because of this 1 over here, 1 is one of those cells, which removes 1 from that cell. The rest of the ones are remove ones from those cells, 1 must be here. Yeah, we do have more clues. So this Dutch Whisper extends all the way over here, at the very least. It could continue extending. My guess is it extends this way to form your L shape, because a lot of the lines here have been forming L shapes. But not for me to guess, it's for me to actually show. Let's keep going. Those 3 digits form a triple. Yes, they do. So they have to be 5, 8, and 9. This cannot be 8. That looks very similar to what we had in this area over here, but we can't do anything there either. Okay. This one was a quadruple. Although I guess 9 can't be in those cells, so 9 can't be... 9 isn't one of those cells. Can we do anything with that? Probably not. Oh, I was gonna say something about 9 being one of those cells. It's not. It could be there, because we still haven't revealed that last digit yet. 9 is one of those cells though. So is 3. And whatever digit that is, I think would be in one of those cells. I can't be sure. Is this where the lull starts to kick in? And I start losing my grip on this puzzle? It might be, honestly, it might be. I don't see anything we could do here at all. I need to actually focus. Oh, it's the 7. Alright, yeah. The 7's over here. Remove 7 from those cells. So 7 must be one of those cells. Therefore, this quadruple is really just 1, 2, 3, and 7. Nice. And we can do a lot of stuff like removing stuff over here. This does in fact form a triple, therefore it has to be 5, 6, and 9. 9 can't be here, forcing a 9 over there, and putting that down. It is a 7, look at that. Okay. Well, that was fun. What else do we have? I don't think anything here can be resolved just yet. I know there's a 2 over there though, like this number is a 2. This forms a 1, 2, 7 triple. Ah, so this is the remaining triple consisting of 5, 6, and 8. And whatever this digit is, it could be an 8, it could be whatever digit that is. Or that. No, well, I don't think so. Whatever it is. Oh, I see. 7 in this box must be one of those cells, which means 7 can't be there. So 7 is now in one of those cells. Can we do the same for other stuff here? No, I don't think so. Sorry, I've returned. I was busy doing something again. I have to do a lot of editing this episode. Okay, so those form a triple, a 1, 2, 3 triple, which isn't very useful because the remaining is a quadruple. 5, 6, 7, 8 quadruple, so not very useful. So now what do I do? Oh, this 3. Sorry, this 3 resolves this 3, 4 pair. And yeah, so it is correct that those do form an L shape. The 4 resolves this 4, 9 pair, which don't give us anything, but we knew that. This 9 resolves this 5, 9 pair, which should do something, even though I don't think it actually does. This forms a triple, yes. 6, 7, 8 triple, which this can't be an 8 anymore. Well, I don't see anything. I really do just assume that this is all there is. This is the last clue, and we are going to solve the puzzle from here. Yeah, 3 in this box. There you go. 3 in this box must be here. There's nothing there, which it's fair, it makes sense. What else do we have? 2? No, 2 is already in the box. What am I saying? We'll figure out the 2 in a lot of other places as well. Alright, that's fair. 3 is in one of those cells. Can we figure this out? Yes, we know that's not a 5. And the reason why is because if it was a 5, then those digits have to be 1 and 9, because those are the only 2 digits that are far away from it. But 1 cannot, and 1 and 9 actually cannot already be here. So this can't be 5. In fact, if this is a high digit, well, those could be 5 though. If that was a 9. Those could be 5. Do they have to be 5? I don't think so. But if those are high, these are generally much lower. They have to be 5 and below. And in fact, 1 is already in the column, so they just have to be 5, 4, 3, or 2. And that digit cannot be 3. Oh, in fact, it cannot be 2, 3, or 4. So that is just a 5 then. Huh. Which means this must be 9. This is the only number that's far away from it. Which resolves all of this. Wow, that is pretty cool. Okay, 5 resolves this 5, 6 pair. Which means that's a 5. Sorry, 5. 5s are no longer in those cells. So 5 in this box, because of this 5, must now be up here. This forms a 6, 7, 8 triple. I was going to say something to do with this 1 and this thing over here, but no, that doesn't even have a 1 in it. That wouldn't help us do anything. Those digits form a 6, 7, 9 triple, but 9 come in that cell, so 9 must go here. This is now a 6 or 7. In fact, this is its own triple. I think this is a 6, 7, 8 triple. This digit now can't be 7 or 8, so that is a 6, which resolves this 6, 9 pair. This 6 resolves this 7, 6 pair. This 7 and this 6 means now that's an 8, therefore that's a 7. This must now be a 4 to finish the box. 8 means that's a 6. That is no longer 8, so that's 7, meaning that 8 is up there. Oh yes, and we are getting through all of this. 8 means now this 6, 8 pair is resolved. Is this resolvable yet? I don't think so. I think we still need stuff from here. That digit though is a 5 to finish the column. Those digits are 2, 4, and 9 to finish the box. This can be 9. That can be 4. Nothing else to do there though. This forms another triple. They have to be 2, 3, and 4. I just think it's 2, 3, and 4. Yeah. 3 means that can be 3. This can be 4. 2, 4 pair here gives us our last digit, which is a 6. Therefore, those digits form a pair, which have to be 7 and 8. And I think that is resolvable. This 8 resolves the 7, 8 pair, which proceeds to resolve this entire set over here. This goes to be 1. That goes to be 7. This 1 resolves this 1, 2 pair. 9 resolves this 2, 9 pair. Well, it's not really a 2, 9 pair, it's a triple. But that is resolved. 4 means this is a 2, 2 means this is a 3. The last digit here is a 4. Whoa, 4. There you go, solving the puzzle in 27 minutes and 53 seconds. Although, of course, with some break because I was busy doing something. But okay, this was actually really fun. It maintained difficulty all the way. And yeah, I had to use some very special logic regarding what the quadruples are. So in its own way, it's also very unique. That's cool, I really enjoyed this puzzle. I hope you equally enjoyed this video. I'll see you guys next time. Bye bye.